Welcome to the video Chapter 11 of Business Statistics. Let's take a look at the OneWayAnova test. I'll be referring to the OneWayAnova table, which is displayed on the screen. This is available in a document accompanying the file. ANOVA testing is an acronym that stands for Analysis of Variance. So just a really quick refresher on what is variance. Variance is the sum of all squared deviations in a data set. So if I have a data value that's equal to 8 and I know that the sample mean is 10, the deviation there would be 8 minus 10 or negative 2, and if I square that and add it up with all the other individual squared deviations in the data set, that gives me a sum of variance, the value of variance. And let's keep in mind that the more widely spread apart a data set is, the resulting higher the variance is going to be. So what our ANOVA test will look at, it's going to compare two types of variances. And let me sketch out a number line here and we'll look at what those two types of variances are. So let's say we have three samples. It could be the number of sales for three separate salesmen over a week. So sample A has a certain value to it, a certain mean, and let's plot that right here on our number line. Sample B, let's say, would fall right about here, and sample C has a sample mean at this point in the number line. So regardless of what the specific numbers are here, sample mean B is numerically greater than sample mean A, and sample mean C is likewise. So at this point we now have our first variance that we're going to consider, and that is called the between variance. So if we computed a variance for this set of three elements, sample means, that would then give us our variance of the between value. Now, the other type of variance that we're going to be looking at is called a within variance. So let's say that if I were to take each of my samples and I plot a confidence interval to estimate that sample's population value. So thinking about what the effective variance is going to have, the wider spread apart that the individual values in sample A are, the resulting wider will be its confidence interval. So we'll say this one has about a medium variance. Sample mean B, let's say, has very low variance, so its confidence interval will be accordingly narrow. And sample C, let's say that it had a really big variance, so its confidence interval would plot out looking something like this. So this graphic represents the two types of variances that an ANOVA test is going to compare, and the variances between means of three or more samples represents the between variance, and will compute a value that represents the overall amount of variation present within the samples summed together. So that is the introduction to ANOVA. So let's take a look now at a sample problem as we work through the rest of the concepts. Here we have a problem that looks at several casino resort communities. So we're told that Singapore and Macau are increasingly competitive with Las Vegas within that industry, and we're looking at a measurement for how many days the average visitor stays. So here we have 3 samples, one from each location, and each of those samples contains 4 individual elements representing a number of days stayed by one guest. So let's perform an ANOVA test with alpha at 5% to determine if the average length of stay was different for the 3 locations. ANOVA testing always looks at, are all of the samples being compared, do they have a statistically equal mean, or does at least one of them have a mean that differs from another? So that's what we're going to be testing here. And you'll notice at the bottom of the table here, I've started us off with a blank template for the ANOVA table. So referring again back to the document that accompanies this video, we'll be using this to complete our ANOVA table. So first thing we're going to do is come up with a few basic sample statistics for our samples. And let's just start things off here by computing the sample size of each sample. Not so much computing, but counting. The Singapore sample consists of 4 elements, Macau has 4 elements, and Las Vegas also has 4 elements. And next thing we'll do is we'll find the sum of all of the elements in each sample. So summation of the Singapore elements comes out to 24, adding 7, 4, 8, and 5. Likewise, summation of Macau comes out to 10 total days, and Las Vegas comes out with a total of 20. Now, having those 2 pieces of information, we can compute each sample's sample mean, 24 divided by 4, 6.0, 10 divided by 4, 2.5, and finally for Las Vegas sample, 20 divided by 4 is 5.0. And while we're working on the basic stats, let's also come up with our overall sample size. In this case, that is the total number of individual elements across all samples. And here, because each of 3 samples has 4 elements, our total sample size, represented in an ANOVA problem as lowercase n, is 12. And we also have an overall sample mean, which in this case is equal to the summation of all of the elements throughout all the samples divided by that overall sample size. So referring to the sum within each of my 3 samples, 24 plus 10 plus 20, we're going to divide that by 12, and that's going to come up with an overall sample mean of 4.5. Alright, having those values, let's come up with our sums of squares values. So when we say sums of squares, we want to think about variance, and remember that the more distance there is between elements, the resulting higher variance there will be. So let's take a look at the first sum of squares value, which is going to be the sum of squares treatments. So we're going to abbreviate that SST, sum of squares for the treatments, and that is going to follow the formula of the sample size of size I, summation that sample size multiplied by the sample mean from each sample minus the overall sample mean squared. And because we have 3 samples, we'll have 3 components going into this summation. So the first sample size is 4 multiplied by the first sample mean of 6.0 minus the overall sample mean of 4.5 squared plus 4 times the second sample mean minus 4.5 squared plus 4 times the third sample mean minus the overall sample mean squared. And once we simplify that down a little bit, we'll have 4 multiplied by 1.5 squared plus 4 multiplied by negative 2 squared plus 4 multiplied by 0.5 squared. And that's going to work out to 4 times 2.25 plus 4 times 4 plus 4 times 0.25, and the sum of those is 26.0. So our sum of squares treatment, which is the value that represents the overall variability within the treatments, in other words between each of the sample means, has come out to have a value of 26.0. Alright, good job on that. Let's move down to our sum of squares error, which is the corresponding measure of variability that looks at the within treatments, within each treatment as opposed to between the treatments. So this formula looks like this. And what it's saying is figure up each individual x value's deviation within its sample, square that value, and do that for every individual value. So we'll go ahead and start jotting this down. So our first value is 7 with that sample mean of 6. So 7 minus 6 squared plus the second value up here, which is 4 divided by, minus that sample mean, 4 minus 6 squared plus 8 and 5 plus 8 minus 6 squared plus 5 minus 6 squared plus, and I'm not going to document all of these steps, so we'll have 8 more square differences to include in this. I'll go ahead and start simplifying this. 1 squared plus 2 squared plus 2 squared plus 1 squared plus the remaining 8 of these. And so we'll have a sum total here of 1 plus 4 plus 4 plus 1 plus, and the 8 other individual contributions. And when we finally finish all the math up on that, we'll have an SSE value of 21.0. So those are our 2 computationally intensive values. Often those will be given to you. The SST and SSE are known to be this, and really once you have those values and plug those into your ANOVA table, the rest is just relatively simple math to complete the table. So good job so far on that. And let's go ahead and start populating our table. I like to start on the left here with sum of squares. We're going to work left to right, and we'll follow the reference formula as referred to on the ANOVA table formula sheet. Alright, so the total sums of squares is equal to the sum of squares treatments plus the sum of squares errors. So 47.0 is going to go here. Degrees of freedom, let's calculate our letter P variable here. So P is equal to the number of treatments, which means the number of samples. So P is equal to 3. We have 3 samples, thus P is equal to 3. So for the degrees of freedom treatments, we're going to want to put in P minus 1, because P is 3, 3 minus 1 is 2. That gives us our degrees of freedom's treatment. For the degrees of freedom error, we want to take N minus P, so N, as we calculated up top, was 12, minus P, which is 3, 12 minus 3 is equal to 9. The total degrees of freedom will add up to will be the sum of the degrees of freedom treatment errors. Also, we could describe it formulaically as N minus 1. So 12 minus 1 is 11, and that completes our degrees of freedom column. Next measure that we're going to calculate is called the mean squares value, and we're going to arrive at this by dividing the relevant sum of squares by the relevant degrees of freedom. So we'll be doing this ratio twice, once for the treatments information and once for the error information. So my SS treatments is 26.0. Dividing that by the degrees of freedom treatments, 2, I'm going to come up with a MST value, mean squares treatments, of 13.0. Likewise, taking my sum of squares error, 21.0, dividing that by 9, which is the degrees of freedom error, we're going to come up with a value of 2.33. So what we've computed now is the MST value and the MSE value. And recall again that the magnitude of the MST value, the larger it is, the more variance there is between the treatments or across the sample means, whereas the larger the MSE value is, that corresponds to having more variance within each sample. So in order to perform this upcoming hypothesis test, we're going to compute our F data value by taking the MST value and dividing it by the MSE value. So 13.0 divided by 2.33 is equal to 5.57. So I now have an F data value for this problem, and we'll look at the hypothesis test for this momentarily. Let's go ahead and come up with our relevant critical value. So noting that my alpha for this problem is 5%, I'm going to go to the 5% F table, and my degrees of freedom 1, which is the degrees of freedom on the top of the table, is equal to degrees of freedom treatments. So degrees of freedom treatments, picking that out of my ANOVA table, is 2, which I've circled here. DF2 on the F chart is the denominator degrees of freedom. That corresponds to the degrees of freedom error, which in this case is 9. So I line up 9 there, line those two up, making sure I'm on the 5% alpha chart, and I get a critical value of 4.26. So I'm now all set to set up and run my hypothesis test for this problem. So let's go ahead and slide this sheet up a little bit, and we'll perform the hypothesis test for this. Any ANOVA test that we perform is going to take the form that's going to say that the mean, and I'll use the specific sub letters here, the mean of Singapore is equal to the mean of Macau is equal to the mean of Las Vegas. So in words, what this is saying is that every mean in each sample is statistically equal to every other mean. And the correct complement to that would be that at least one mean does not equal another, or something to that effect. So any ANOVA test will say that all of the means are equal to each other as its null hypothesis, and the alternate will always claim that at least one of the means differs from another. So I'll go ahead and work my 7 steps for this test. The type of test we're going to use is a OneWayAnova F test. And now for my data and crit values, I've already done all the hard work on those. So I look up here to my ANOVA table. My data value is 5.57. My crit value is 4.26. And my rejection rule. So let me go ahead and sketch this distribution out, because this is an F distribution. It's one-sided, starts at 0, only goes positive, and I've labeled my critical value as 4.26, and I now know that the rejection region consists of the area of where the F value is greater than or equal to 4.26. So I'll write that for my rejection rule. Reject H null if F data is greater than F crit. And in this case, F data is greater than F crit. My F data is 5.57 compared to the F crit of 4.26. So my decision here is to reject H null. And finally, that allows me to say that there is evidence that at least one mean differs from another. And that now concludes the primary portion of this ANOVA test. The finding is that there is sufficient evidence to support the hypothesis that at least one mean differs from another at a 5% alpha, and therefore that's our finding. Now let's take a look at one more test that we can do for this problem, and what we're going to do is we're going to look at a procedure that's going to allow us to decide which specific sample means differ within their pair and which are found to be the same. So let me jot down a formula for this. And this is going to be a confidence interval formula that takes this form. We're going to take the difference in sample means, so those are available from the summary stats that we computed earlier, and we're going to compute the difference and put a corresponding margin of error on it, and that margin of error is going to be Q alpha multiplied by MSE divided by M. Here M represents the sample size in one treatment, both of them having the same sample size, and also we're given our Q alpha value in this case. So the appropriate Q alpha value is 3.95. So therefore our margin of error is 3.95 multiplied by the MSE 13 divided by the sample size and the MSE of course is 2.33, and we're going to divide that by the sample size, 4, square root that. Doing the math on that, we get a margin of error of 3.01. So let's list over here our 3 combinations that are possible with 3 samples, and the difference in these is 6.0 minus 5.0, 2.5 minus 5.0. So that's going to give us a sample mean difference, which is what this is, of 3.5 for this upper pair, 1.0 for the center pair, and finally negative 2.5 for the lower pair. And for each of these, let's add and subtract this margin of error to this. So the first pair would be 0.49 positive to 6.51 positive. And what we want to do here is ask ourselves, does 0 fall within this interval? If 0 does fall within this interval, it would be reasonable to expect that the difference between these 2 sample means would be 0, and thus they were statistically equal. In this case, however, 0 does not fall into this interval, so therefore we can state that the means of Singapore and Macau differ statistically. In completing these confidence intervals, we see that both of the remaining intervals do have 0 within their interval, and thus we can say that there is evidence that because these do not have 0 within their intervals, that these pairs differ within their pair, and that will complete the problem. Thanks for watching.